Alright, so in this lesson, we're going to talk about average acceleration and then instantaneous velocity and speed. So first we need to define what acceleration is. So acceleration is a vector, okay, that means it has a direction. It is also the rate of change of an object's velocity. Rate of change means I've got to take time into account when I look at it. So acceleration is how fast or how slowly the velocity of an object changes. It also has to have a specific direction. Why? Because it's a vector. So definition of acceleration is it is the rate of change of velocity. Rate of change, we divide by time. The symbol is lowercase a. It's got to be a baby case, baby a, not a capital A. Capital A stands for something completely different. It's measured in meters per second squared. So meters per second per second. We only deal with constant acceleration. That means there's a constant change in velocity in every equal time period. So in other words, the velocity changes by the same amount, the same meters per second, every second. And that's either that the velocity is going to increase or the velocity is going to decrease. So from the definition, acceleration is the rate of change of velocity. Now these symbols are nothing new. You've seen all of these in some point. Change in means final minus initial. In this case, it's change in velocity. Acceleration is meters per second squared. Delta V is change in velocity, okay, which is measured in meters per second. T is time, okay, delta T. VF, new symbol for you, final velocity. VI, initial velocity. Okay, and it's always final minus initial, always final minus initial. So if something's slowing down, you're going to get a negative acceleration because you'll have a small number minus a big number. We get positive acceleration. So here we have a car that's traveling on a long, straight, horizontal road. Its velocity is recorded every second. And what they see is that its velocity goes from 4, then to 8, then 12, then 16, then 20, then 24. And if you look very carefully, the car is moving 4 meters per second faster every second. 4 meters per second per second. It's accelerating. So the final velocity is bigger than the initial velocity. So I'll be going a big number minus a little number, which makes my acceleration positive. If my acceleration is positive, it means it's getting faster. And it means that my acceleration and my velocity are in the same direction. That's like when we're in a car and we put our foot on the accelerator pedal and then the car goes faster. We're giving an extra force. We're putting a force in the direction that we're trying to go. So it goes faster. So we're increasing the velocity. It's accelerating in the positive direction. We also get negative acceleration. Now, sometimes you guys like to describe it as deceleration. We don't use the word deceleration. That very much is an English term, and we know as part of a language, everyday language type thing, and often we'll go, it's decelerating. What we mean is that the velocity is getting smaller, okay? And that's fine. I know that's what happens, but we don't describe it as that. So if we take the same car, but now it's slowing down, so they're putting their foot on the brake pedal. It was going at 20, then it's going at 17, then it's going at 14, then it's going at 11. And we can see that every second the car's getting slower. And it's moving slower by 3 meters per second every second. So now my final velocity is smaller than my initial velocity. This is going to mean that my acceleration is going to be negative. because my final number is smaller than my initial number, okay, so I'm going to have a small number minus a big number. And you know from maths, a little number minus a big number gives me a negative number. So now it's slowing down and it's in the opposite direction to the motion, okay? It's negative. So now acceleration and velocity have opposite signs. And that's fine because the sign gives me direction. So let's look at an example quickly. Susan starts from rest. Rest means that my initial velocity is 0. It's not moving. After 5 seconds, so that's my delta t, she obtains a velocity of 7. So that is my final velocity. So she had an initial velocity of 0. She has a final velocity of 7, and it takes her 5 seconds. And they want her acceleration. So we know that acceleration is change in velocity over change in time. We're going to take this is final velocity minus initial velocity over time. That means we're going to get 1,4 meters per second squared. It's positive. Now, I can't say left, right, up, down because I don't know. All right, I also can't say north, south, east, west. But I do know that she's going to go forward, so I write the direction as forward. That is still a direction. And her acceleration and velocity are in the same direction because they're positive. Same, Susan is now traveling, all right, we don't tell you how, it doesn't really matter, at a speed of 10. So that's my initial velocity for this question. When she suddenly has to stop, it takes her 6 seconds, so that's my delta t, for her to stop. That means final velocity 0. They want her acceleration again. Let's write down everything we know. VI is 10 meters per second. VF is 0 because she stops. Delta t is 6 seconds. A is what we're looking for. And again, acceleration is change in velocity over change in time. Final velocity minus initial velocity. Doesn't matter that we get a negative. This negative is very important. This negative tells me the acceleration is in the opposite direction to the direction that it's moving in. So it has to slow down. That means we have 1,67 meters per second squared in the opposite direction. Here you could have said backwards, because she's moving forwards and the acceleration is backwards, and that's like when you put your foot on the brake in a car or brakes on a bicycle, okay? So we need to remember we must always have a positive answer at the end with the direction in words. We never put a direction in words with a negative answer. You need to now work through activity 1 on page 228. Look at question 4 and 5. Okay, the answers are in teams. You really need to pause now, go do that, and then come back to the video. We're going to do this all together now because it's in the next unit's small. Unit 6, instantaneous velocity and speed. We've looked at average. Okay, so now I'm going to remind you. Average velocity is the rate of change of position. And average means that we take the whole distance divided by the whole time. So we're using big volume, big values of time, okay? And remember, well, average velocity, your V needs a little line on top of it, okay? Because that means that it's average. So we have average velocity divided by the, which is going to be the horizontal displacement, divided by the time. But now this displacement is the whole displacement. It's the whole motion. And you need to remember that if something's accelerating, then at some points in the motion, it's going to be going slowly, and then it's going to speed up, and then it's going to go faster. So this average is looking at the motion as a whole. sometimes we need to know the instantaneous velocity. Now, this is also the rate of change of position, but the time is incredibly small. So to get instantaneous velocity, we're talking about fractions of a second. It's actually really difficult to calculate instantaneous velocity with normal everyday calculations. Okay, there are ways to do it with graphs, and we are going to show that to you. Instantaneous speed is the same concept as instantaneous velocity, except there's no direction. So now the speed, instantaneous speed at any point in time, is the same magnitude as the instantaneous velocity. Velocity, remember, is a vector, so this velocity needs to have a direction. All right. In this section, this is all you need to know from Unit 6. You don't need to know anything else from Unit 6. Unit 7 is an investigation on uniform acceleration. We will do this as a practical in Term 3. So don't stress about Unit 7. And that's all for this lesson.